All right, section 4.2 is going to introduce us to yet another sort of notation. We have seen it before. I know you've seen it before, but you probably haven't used it very much. So if it feels a little bit uncomfortable to you, that's probably why. These are going to talk about the sigma notation. So here's your first definition or first description of what's going on. So we're going to take a bunch of terms, A1, A2, A3 to AN. Okay, so there's a list of numbers. Those are all representing numbers. And we want to add them all together. That's the goal, is to take this list of numbers and add them all together. And the notation for doing that right here is this sigma notation. So you'll see the number underneath tells you where you start, I equals 1. So the subscript starts at the first term 1. And it goes up to however high we want to go up. Usually the n will have a number up there. It will say something like 12 or 200 or something like that. So we start, the bottom value tells you where you start, the top value tells you where you stop. You don't always start at 1, though you often do. So you want to be paying attention to the top and bottom value. And then it tells you that you're going to add up these types of terms. There's often an equation in there, so it might say something like 3n. 3n squared plus 2, or something like that. Okay, so there's an equation where I've circled in red usually that defines for you how you get these terms. And then the process is you want to add all the terms together. Okay? Now, if you don't have very many terms, this isn't a big deal, right? I mean, if I had 6 terms, I just add 6 terms together. If I have 200 terms, I don't want to add 200 terms together. So the first thing I'm going to show you is how we could deal with this when we have a small number of terms. And then I'm going to show you a process by which you can deal with it when you have a larger number of terms. So the kind of two things we're going to look at. I is called the index of summation, index of the summation right here. A sub I is just the ith term. That sounds really awkward to say, but if it said A3, it would be the third term. If it said A with a subscript of 12, that would be the 12th term. And then the upper and lower bounds are these top and bottom numbers. So this bottom number is a 1, and the top number in this case is an n. So the 1 is considered the lower bound, the n is considered the upper bound, and like I said, the n is usually given to you as a number itself. It's not left as a sort of arbitrary value. Okay, so you've already got one on your paper. Oh, let me show you one other thing. By default, sometimes you will see this written like this. It's not really that it's any different, it's just what the computer is able to deal with. So on your notes, what you're going to see is problem number 1, and it's going to look like that, right? Where the number looks like it's sort of to the side, not above and below. That's what Word does to it when I put the number 1 in front of it, telling you it's the first problem. But then if I delete the number 1, it puts it back into the form that you see circled in the middle of the screen. There's absolutely no difference. It's just a formatting issue, okay? So you can see that on here, that number 1 didn't affect it because it wasn't done within Word, but on your paper it did. I just don't want you to think that that means anything different. It doesn't. All right, so what you see is you see the lower bound, I equals 1. You see that the upper bound is 6. So we're going to have how many terms? 6 terms. Our 6 terms are going to go from 1 to 6, okay? And we've got what looks sort of like an equation, 3i minus 2. Everybody good so far? All right, so what we're going to do, because this is a small number of terms, is we can actually find out what is the first term, what is the second term, and so on. So we're going to actually find a few of these, and then you're probably going to notice a pattern, and we can just use the pattern to find the rest. So A equals 1, or A with the subscript of 1, I mean, means that the I value is 1. So this is 3 times 1 minus 2. Okay, it's just telling you, this subscript tells you what I equals. That's all it does. So what is 3 times 1 minus 2? 1. Thank you. All right, let's do A2. Okay, so this is 3 times 2 minus 2, which is 4. We'll do A3, which is 3 times 3 minus 2, which gives me 7. We'll do one more. 3 times 4 minus 2, and that gives me 10. And you could continue, if you'd like, in the same way for A5 and A6. But you could also notice over here, and not always will you be able to, but sometimes you can, there's a pattern. What's happening if we get from each term to the next? You're increasing by 3. Do you know why? Do you know why that's happening? because of this 3 multiplying in front. That's why that's happening. So the minus 2 stays the same every time, but we've increased it by 3 every time because that 3 is multiplying by the number. If you happen to recognize that, it would be perfectly fine then to write down that this is 13. And then, what do we have? 16, right? Okay, so we've listed out the first 6 terms. What we want to do then is we want to add them together. So I want 1 plus 4 plus 7 plus 10 plus 13 plus 16. And that is the summation of the first 6 terms. So grab a calculator if you want, or add things quickly in your head, whatever makes most sense to you. And somebody tell me what you get. I think it is 51. Did anyone else try that real quick? Yep. Okay, good. We got a couple people, 3 people now saying 51. Yep. So this is 51. So this is pretty straightforward, right? I mean, aside from the notation, which looks a little weird at the beginning, this is really just addition and multiplication. Agreed? Okay. Now, like I said, if we had more than 6 terms, like we had 200 terms, this would not be a particularly friendly way to do the problem. Agreed? Even if we did notice a pattern. I don't want to write down this pattern 300 times or something, right? So we've got some methods to be able to actually simplify the process. So we're going to look at 5 rules or 5 properties of summations. So we've got n as a positive number, so the n is the top value. And we've got c as a constant, so c is just a number. So think with me, if c is a number, let's say it's just like the number 5, and I find the first term, what's the first term? You know, like if I had, oh, sorry, I said a because you said a. I equals 1 to 12. What would my first term be? What would ai be? 5. AI, A1 is what I meant to say. What would A2 be? 5. What would A3 be? They'd all be 5, right? Because there's no variable to put the number into. There's no letter here. There is no I in this value. So every number is just 5. So this is just a series of 5s. Okay, so what would you do? Well, you'd just be adding a whole bunch of 5s together. How can you add the same number together a whole bunch of times much more efficiently? Right, you multiply that number by however many of them you have. And how many of them would we have in the problem that I sort of just set up here? N. And it's 12 in this particular case right here, right? It's whatever the top value is. So this is actually just a multiplication problem. So when I've got a summation of just a number, right, this is actually just that C value times N, because it's done multiple times. Now the rest of these, your book is going to justify each of them for you. I just thought that one's pretty straightforward. We can see why that's happening. But there's proofs in here for the other ones. If I have just the value I, think about what we're actually doing. If this is just I, the first term would be 1. The second term would be 2. The third term would be 3, and so on. So this is adding something together multiple times. But it's not the same number, right? It's increasing number. So I'm going to add 1, 2, 3, 4, 5, 6, 7, all the way up to n. That actually has a really nice form. A gentleman by the name of Gauss was one of the first ones anyway to be credited with the development of this formula. This is n times n plus 1 over 2. So this is the sum of the first n positive integers. The second one, they're all squared. So, right, like this is 1 squared plus 2 squared plus 3 squared plus 4 squared. We're adding all the squares up together instead. And we're adding the squares together. Its formula starts out looking a lot like the one from before, n times n plus 1. But then it's times 2n plus 1, and it's over 6. Again, there's actually a proof for that formula in your book. So these are the first 3. I'll show you how we're going to use this to be helpful to us in a minute, but these are the first 3 formulas we're going to need. The fourth one and the fifth one are sort of written as a combined rule in your book. I just decided to separate them out because they look a little bit more like things we've seen before if we do that. This one right here is a constant times a constant times the variable that's changing, the number that's changing, right? Okay. So when we've got this, it's very much the same thing as if the constant weren't there and it were multiplied in the end. So no matter what AI was, we could find the summation, and then we could multiply by the c at the end. And we're going to see this property happen as well. So this happens like with derivatives, right? When I want the derivative, the constant to the beginning that's multiplied doesn't change, and then I take the derivative of the other piece. It happened when we talked about antiderivatives. The value at the front doesn't change, and the value afterwards with the variable in it, that part we take the antiderivative of. Right? We called it a constant multiplier rule. It happens here again. Okay? And we're going to see it happen again one more time later on. And then this one looks a lot like our sum and difference rules. In fact, it could have had a minus in the middle there. That would be fine too. So what do you think we can do with this one? History would tell us we could do what? Yeah, that's what we did with derivatives, right? We took the derivative of each one separately and then we added them or subtracted them. We did it in the last section with antiderivatives. We took the antiderivative of each one of them separately and then we added them. And we can do the same thing here. We can take the summation of each one individually, and then we can add them. These two rules are almost, especially the second one, the summation one, you probably would have done it and not even realized, hey, I used a rule. Had I not told you there was a rule that said you could do it, you would have done it anyway. You would have just sort of assumed you'd been able to. And it is true, you are able to do that, but I wanted to formally tell you that that's actually a legitimate operation. It's not just like you're making things up so that it works out nice. Okay? Ready to do a couple? All right, so we're going to do the summation from I equal 1 to 16. Granted, we could write 16 terms out. It wouldn't be the end of the world, right? But if we could do it in half the time, would you not vote for that direction? I would. So I'm going to show you how to do that. I don't know if it's half the time. I totally made that value up right there. But it's definitely in less time, okay? So what this process that we did with those 5 rules or properties before tells us is that I can rewrite this with the 5 in front. And this would be the summation from I equal 1 to 16 of just I. And then minus the summation from I equal 1 to 16 of just 4. So we're separating all the pieces apart. It almost has the feel like you're distributing the summation somehow. It's not really what's happening, but it almost feels like that, doesn't it? The 5 comes out to the front. The I is the variable, so it stays put. The subtraction is here like the addition was on Rule 5. And then we have the summation of just the number 4. Now, each one of these is a different property. So this one right here, which property is it in your list of 5 properties? I should identify just this piece right here. Just the part that's the summation of I. That was the second one. So this is property number 2. And then this one right here where I have the summation of just the number 4, what property is that one? That was the first one. This is property number 1. Okay, can everybody identify those pieces looking like what they were before? Okay, so the 5 is going to stay put. And what's going to go in this spot right here is we're going to take a look at what property number 2 said. Well, property number 2 said I was going to take the value n plus 1, and then divide by 2. Right? And I'm going to write over here just to remind us here, n is 16. We're going to put the 16 in a minute. But I'm just going to write sort of the generic form for it so you can see it sort of just being pulled in directly right here first. If you do them at the same time, that's great. And then on the second one, property number 1 says I can take that constant and I can multiply it by n. And in this problem, n is 16, so if I replace the letter n with the 16s everywhere, I have 5 times 16 times 17 over 2 minus 4 times 16. And you can let your calculator do all of that for you to give you a summation value. Grab your calculator, multiply, divide, add, subtract, all that good stuff. And somebody tell me what you get. $616. Micaiah got 616. Brooks? Yep, good. All right, so we've got 3 or 4 nods now saying 616 works out. Okay, any questions on that? Was it quicker than writing out 16 terms and adding them? I think so. And it'll be even more quicker. I think the right word's quicker. It'll be even quicker as you do them more because you'll be more comfortable with the properties. So let's try another one. What do you notice about this one that's different than the last one? There's a couple things. It looks like it's multiplied, right? And you don't have any properties that tell you what to do when the value is multiplied. So what we're going to have to do then is to distribute them. In this case, you called it FOIL. We don't actually have binomial, but we're going to distribute, right? Yeah. What else do you notice on this one? The n value is really high, isn't it? 140, I really don't want to write 140 of these out. No question on this one. Okay, it's not just a matter of, hey, it's going to be a little bit quicker. It's a lot quicker. So let's take a look. We're going to do exactly what Brooke said. The first thing we'll do is we'll recognize that I can write this down, and it's in terms of n, which is also a little bit awkward actually, but n starts at 1 and it ends at 140, and the term is n squared minus n, if I distribute it, right? All right, so we're going to separate these. I'm going to write it sort of in parentheses like this to recognize, but we're going to separate these with the summation rule, right? This is sort of property number 4 allows us to separate this. This is a summation from n equal to 1, from 1, excuse me, to 140 of n squared, minus the summation from n equal 1 to 140 of just n. And the bad part about this is that we're sort of using n as multiple quantities in this case. Let's actually give this a different name so just I can call it something different. Let's call this 140 at the top not n, which is what we have been using. Let's call it something else. Could we use k? Is that all right with you guys? So let's say that this goes from n equal to 1 to n equal to 140, which is actually going to be my k value. So here's why I mention that, is because the rules that we have are all dependent upon the thing on the top that we'll call k now. So this particular property is property number 3. Agreed? And this one right here is property number 2. So on property number 3, we should be taking the top value, which we're calling k, times k plus 1, times 2k plus 1. Or if you want to go ahead and put in that k is 140, you could do that. And what do we divide this one by? 6. And then on the second one, we're supposed to have k times k plus 1, or 140 times 140 plus 1, over 2. And as we identified over here, k is 140. It's kind of funny looking 4. All right, so we actually have 140 times 141. 140 times 2 is 280, and then plus the 1's 281, right? So this is times 281, all over 6, minus, and then I've got 140 times 141 over 2. It might be easier for your calculator for you to do each of these separate and then subtract them. So find out this value, find a number, find this value, find a number. You can do otherwise, but just in case you make an error or something like that. These numbers are kind of large numbers this time. Move it up just a little bit. I have 92, 44, 90. So 924,490 minus 9,870. But please check to make sure I did that right. I did it late last night. Did I get them right? Haven't tried them yet. Grace, did you get them?
I did it all together.
Okay. What did you get for your final answer? Okay, good.
14,620.
I got the same number.
Excellent. Thank you, Micaiah. And then did they subtract to give you the same thing? 914,620?
Yeah.
Excellent. So this summation is really big. I mean, 900,000 is a large value. All right, any questions on that? Okay, so you'll notice the homework's not exceptionally long. You're just going to be practicing these particular types of summation properties.